How about now?
So good evening, everyone, and thank you for joining us tonight for a technical talk on human-robot interaction. I am Sanjaksha, co-organizer of Women in Robotics with my friend Harini, and we have Gianna for volunteering and to help with the event. So yeah, a little about us. Women in Robotics is a nonprofit organization founded by Andra Kay at Silicon Valley Robotics in California, and this is the Boston chapter of Women in Robotics. We are a professional network for women who are working or aspire to work in robotics. Anyone in any professional background who supports our cause is welcome to the group. We'll share the sign-up link in the chat. And we also want to thank our Zoom sponsors, Vecna Robotics, for their constant support. So today we have Dr. Marynel Vázquez, assistant professor from Yale University, Computer Science Department, to tell her more about her research in advancing multi-party human-robot interaction. She focuses on both studying social group phenomena and developing perception and decision-making algorithms that enable autonomous robot behavior. Marynel received her bachelor's degree in computer engineering from Universidad Simón Bolívar in 2008 and obtained her MS and Ph.D. in robotics from Carnegie Mellon University in 2013 and 17 respectively. Before joining Yale, Marynel was a collaborator of Disney Research and a postdoctoral scholar at the Stanford Vision Learning Lab. So check out her lab, Interactive Machines Group. We also will be sharing the link in the chat. And Professor, thank you so much for joining us today. How are you feeling?
Good. It's a pleasure to be here. Thank you so much for the invitation.
Yeah, we are really excited to learn from you today, and over to you.
All right, so thank you all for coming. Today I want to tell you a lot about our research, but before I get into the sort of details, I wanted to start this presentation by telling you a little bit about sort of the field of human-robot interaction broadly, and then I'll dive into specifically what we've been doing. And so to start with that, I want to mention 3 trends that I've observed in the field over the past 10 years or so. And the first one that comes to my mind when I think about HRI is that there has been a very strong transition from studying human-robot interactions with Wizard of Oz methodologies to trying to study these interactions with autonomous systems. And so if you're not familiar with Wizard of Oz, the way this works is that you would have a robot that is interacting with a person, as you see here on the right. And perhaps that robot is not fully developed, it's not fully capable as you want. And so instead of first, developing that autonomy, what you do is you have a person that serves as a secret wizard operate the robot while it interacts with people. This is why we call it Wizard of Oz. And of course, right, this type of methodology was amazing to get the field started because we could very, very quickly test different robot behaviors and in different situations with different people, while robots were, kind of not very good or work well enough to sustain these interactions. But the reality is that there's only so much you can do with these studies because at the end of the day, right, what you're really studying is an interaction between the person, the robot, and the wizard, not necessarily sort of the human-robot interaction that you originally intended. And so that has pushed a lot of technical work in HRI to try to actually be able to study the systems with 100% autonomy or as much autonomy as you can possibly can, such that hopefully, what you're studying is actually what you would see if that system was running on its own. Now, the second trend that I wanted to mention today is that running these systems for a while is really, really challenging. So it's, way more practical to study short-term interactions. And a lot of the work that you've seen in the field oftentimes focuses on interactions that last, between a few minutes to perhaps an hour. But oftentimes people have realized that, well, people generally get excited about robots. And there's a lot of a novelty effect that happens in these short-term interactions. And this has sort of naturally driven people to ask, well, what if you had a robot sort of, deployed for a week, for a month, for a year? How would things change in those situations? And, I think personally, this trend has been really important. I personally have not worked on long-term interactions yet, but it's very important because, when you think about robots in human environments, this is probably a lot of what you're going to see, right? A robot in a home with an elderly person, they're going to see each other a lot over months, over years, perhaps. Robots in workplaces, they're going to see the co-workers a lot as well. Perhaps robots in homes that are helping teach with, particular learning lessons that they need to practice for school, or maybe robots that help with art, like you see on the bottom right. All of these robots that are not just going to be interacting with people for a few minutes, but chances are it's for long periods of time. And so, these pictures, they make me really excited. And hopefully they make you really excited too, about what the future of robots can be. But the reality is that there's one thing that is missing. And that is that oftentimes there's not just a single user in these environments, right? Oftentimes the world looks more like this. And so this is actually what the third trend that I wanted to mention about today is all about, which is a push from studying one-on-one interactions to studying group interactions, right? How do robots deal with the fact that, there's multiple people around that want to talk to them when they're navigating, there's multiple people and groups that are happening. And so that's actually what most of our research is about. And so from an academic perspective, what we ask is, how can we enable robots to operate in complex social settings with and around multiple people? And, I'm selling you this from an academic perspective as a question, but in my vision of the future is I want to have robots everywhere. And chances are there's just going to be a lot of people around. And so how do we make that happen? How can we get there? Now, you might be thinking, if you haven't worked on this problem yet, that, well, groups are easy. They're just a generalization of one-on-one interactions. And I would argue it's not that simple. And so, for instance, if you think about these different environments where you could imagine having robots one day, right? Think about robots in schools, in theme parks, in medical settings, in busy streets. The first things that happens as soon as you have a lot of people is that from a systems perspective, sensing becomes more difficult, right? The data that you're going to get from your sensors is going to be just naturally more noisy and incomplete because of occlusions and so on. Now, on top of that, the more people you have around, the more dynamic human behavior is just going to be because people kind of, compound on each other and the effects that they can have on their behavior. And so to bring an example here, this is a very short clip from a study that I did as a PhD student at Carnegie Mellon in collaboration with Disney Research. And what you're seeing here is a robot from the top, looks like a box. It's meant to look like a furniture robot. And you can see also kids that were interacting with this robot that came to the lab to test out a couple of different technologies. And we had made this robot to kind of, be the last goodbye, giving them a souvenir, a photo from a prior activity, which is what you see in their hands. Now, we roboticists, we thought, oh, kids are going to be all excited with the robot. They're going to be engaged with it all the time. And guess what? That was not the case. So here, this is a group of 3 children, okay? And the one that I'm highlighting right now, he was definitely interested in the robot. He got his souvenir. He has this paper in his hand. But he was just not willing to engage with the robot in a typical conversation, okay? And if you think about it, right, if this had been a one-on-one interaction with that kid that has the white shirt that was walking, if he had left, the interaction would have been over. So he was sort of naturally forced in that situation to stay there to keep the flow of the conversation going. But in this case, we had 3 children. 2 of them, as you saw originally, were fully engaged with the robot. They kept the conversation going. So this one, it was okay for him to just walk around and keep watching and so on. And these are the kind of things that you just never expect if you're living in the, one-on-one interaction world, because it just never happens. Whereas in the group case, there's all sorts of behaviors that come up that you wouldn't otherwise see. Now, last but not least, it's important to say over and over that robots influence human behavior, even if robots are the simplest thing possible. And to show this, I'd like to show this video by Madeline Gannon, who you can see behind the computers on the far right. This is an installation that she was working on. And in particular, what happened is there was a very big robot manipulator in the middle. Then there was this sort of cage around it to make it safe for people. And people would come and approach it, and the robot would kind of turn towards people and kind of move a little bit towards them a little bit randomly to kind of engage with the installation. Now you see this installation and you think about the control software for this robot, and it's very simple, right? You're tracking people, you're just moving the robot towards them. And in return, you get all sorts of reactions from people, right? And so when you think about the fact that robots influence human behavior, and on top of that, you have multiple people and people also influence each other, well, this problem kind of becomes really hard. And so our particular view on how we can sort of think and address about these challenges is a very interdisciplinary view. So we like to think about human-robot interaction from these three perspectives: from a kind of classical robotics perspective, a computer science perspective, oftentimes when we're thinking about the brain of that robot, and from a design and human-centered research perspective, when we want to make sure that what we're developing sort of makes sense for people. Because after all, right, this is very important for human-robot interaction. And so we've done a lot of sort of different projects in different areas at the intersection of each of these components. And what I'm going to do today for the remaining minutes that I have is sort of walk you through a couple of different examples that combine different aspects of our work, just to show you how you could perhaps tackle these problems, and to get you to think a little bit about the challenges that come up in these types of interactions. Okay. And so let me start first with talking about social group phenomena, because this is something that is very particular to group interactions. And so the first and second idea I want you to take from this talk today is that studying group phenomena in HRI is important because, one, it provides novel mechanisms to drive group dynamics, and two, it allows to computationally abstract some of the complexity of group interactions. And so let me go and give you an example of point one. So group phenomena provides novel mechanisms to drive group dynamics. So a few years back, this video was published at HRI, at the HRI conference, and many people were really surprised by it, including myself, because we never imagined that a robot like the one you see here in a public shopping mall environment in Japan would be treated so poorly by children in this public environment. And so as you saw, here in this video, kids were, hitting the robot, kicking the robot, doing all sorts of things to it, which, you kind of really, at least I didn't expect. Now, since then, there has been a lot of attention to people mistreating robots. And this is just a number of articles that you can find online today. And the reality is that robot abuse happens. This is not necessarily an isolated sort of event. And, from my perspective, this is not ideal because, I want robots to help people. And if robots are mistreating robots, like say the examples that you see here, chances are robots are not going to be able to help people back. And so that sort of defeats the purpose of having these machines around. Now, for robots, this is a big problem, right? Because rule number one of robotics is robots should not do anything to harm people. And so robots, in principle, they can't really do anything if the kids are, hitting it. And so what can they do? Well, we thought, robots, yes, themselves, they cannot do anything directly, but they are in a human environment. So maybe they can leverage their social context to mitigate abuse. And by this, I mean, maybe they can induce human bystanders, other people, to intervene if something is happening to them. Now, this idea is not necessarily new because bystander intervention is actually a key technique that is often used in schools for, preventing bullying and helping deal with these situations in human-human interactions. And so we thought, well, maybe, we can translate this to the context of robotics. And so to test this out, we decided to run a study where we had a confederate, which is the person that you see here in black. We had a participant, which is the person that you see here in the right. And we also had a robot that would respond empathetically to how they were doing on a task on the tablet that you see on the table, okay? Now, this task was designed such that the confederate would perform poorly. And whenever that happened, the confederate would sort of, discharge its stress on the robot, okay? And this happened in a gradual manner where at the beginning of the study, the confederate sort of verbally mistreated the robot, and then later on it did so physically. And so let me show you here an example. This is the example of verbal abuse.
Ah, piece of shit. Yeah.
Do you hear the audio? Yeah, great. Okay. So now I'm going to show you the example of physical abuse. And so what we wanted to see at this point was, okay, the confederate had mistreated the robot. Would different reactions from the robot motivate people to intervene and say something to him? Okay. Now, what we found was that most participants turned the robot up after the last mistreatment, which was when it was thrown on the table. And so that kind of, was a positive result. People are willing to help the robot to some extent. However, only 27 of 48 participants made some verbally discouraging comments. And out of those, only 2 directly intervened or questioned the action. So for example, one said, "You probably shouldn't do that." Another one said, "Does it really bother you that much?" And, at the time we were thinking, motivating people to intervene is hard. Maybe because we just don't like to engage in conflict, right? You just don't really like that. And later on, I learned about this study about conformity in human-robot interaction. And conformity, if you haven't heard about it, is a type of social influence involving a change in belief or behavior in order to fit within a group. So, whenever you're in a group and a bunch of people says, "Oh, we should do this," you internally don't agree, but you kind of go with everybody else to kind of be part of the group. That's when conformity is. And so given that, there was evidence that this type of effect may happen in human-robot interaction, well, maybe we can leverage this type of, group influence to induce pro-social interventions in HRI. And so we decided to try this out in another study where now the participants were working collaboratively to build the structures that you see on the right. And so here, the timeline, what you had was that participants were collaborating to build a tree structure, a fort structure, a pool structure, and along the way, the robots that were on the table were indicating pieces to use to kind of keep building this structure. Now, one of them in particular, the yellow robot, made mistakes, pointing at the wrong thing. And when that happened, the confederate abused the robot, okay? And so let me show you an example of what that looked like.
Oh, gotcha, okay.
So here they're building the tree.
Okay.
Now the next piece is green, but the yellow robot is pointing towards blue.
Oh.
It's just being stupid.
And this was a mistake. They both realized it, that blue is not a piece that you should be using in this step. And later on, the confederate on the left, mistreated the robot, kind of similar to a prior study. And so in this case, the yellow robot was the one that always made mistakes. And it always responded the same way. So it basically shut down for a few minutes after the mistreatment, as you can see on this video. And after some seconds later, it came back on. Now, what we were really studying here was how the behavior of the other robots on the table could influence, or whether they influence, the participant. And so in one condition, in the video that I showed you before, the other robots ignore the abuse. In the other condition, in the experimental condition, the other robots turned towards the abused robot and expressed sadness after the mistreatment. So now the other robots are turning, and they're expressing sadness towards the mistreated robot. And so what we saw in this case was that in the experimental condition, the sad response condition that you just saw, there were more interventions from the participants in terms of the mistreatment that was happening. And this was not only in terms of just the plain number of interventions, but actually there were more participants that intervened at least once to either interrupt the abuse script, to direct requests to stop the abuse, or to say verbal comments that induce social pressure that put the Confederate on conflict, you know, about whether to continue or not. And so let me show you an example of this. And so hopefully you could hear in that video when the Confederate on the right started, you know, sort of mistreating the robot there, the participant on the left was like, whoa, 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 don't break it, don't break it. And to me, this was, you know, particularly impressive to see because, as I said before, right, engaging in this type of conflict is difficult. And somehow, right, these two conditions, there was a very clear difference in terms of what was going on. And so to me, that was really exciting, right? A way to think about how group phenomena like conformity can perhaps be used to drive group dynamics in HRI. Now, I'm going to talk about this second point here, which is that group phenomena allows to computationally abstract some of the complexity of group interactions. And so bringing you back to the time of my PhD, you remember this study, right? We expected all the kids to engage with the robot for the full time of the interaction, but that was not the reality, right? Several of the conversational members changed throughout the interaction, and even new conversations started right in front of a robot when it had absolutely no way of recognizing what was going on. And so at the time, right, we were thinking, well, what can we do to enable a robot to know who's part of its conversational group? And maybe the first thing that you would think about is audio, right? Can you hear who's speaking? And that could make sense in many scenarios, but if you're in a noisy place, maybe that's not the best sensor to use. And so we thought, well, it looks like people are standing in very repetitive ways when they're talking to other people. Maybe we can use that. And so it turns out that you know, work in social psychology has shown that when people engage in social conversations in open environments, they tend to stand, just like I said, in very repetitive patterns, just like the ones that you see here. For instance, you might stand face to face with someone else, or maybe in a semicircular formation. And the reason this happens is kind of very intrinsic to how we're wired. On the one hand, right, we want to be close to other people so that they can hear what we're saying, we can hear what they're saying, but at the same time, we also want to make sure that we can predict whether the message that is being transmitted is actually being received effectively. And sort of that naturally leads to these types of formations. Now, in HRI, we've shown that these types of formations also emerge pretty much naturally without you telling people how to stand relative to a robot or anything like that. So long, at least, as the robot has a clear forward side, right? If you cannot tell where the face of the robot is, well, chances are this model does not necessarily translate to that. And so, given that this type of formations emerge in HRI, what we thought is that, well, if we can detect these formations, then robots can use them to identify who's part of their conversational group, right? Because they're very prototypical of these interactions. And so how you may do that? Well, here's one particular approach. Imagine that you have a socialist scene where you know there's people, you know at the very least their position and orientation. You can build a graph out of that scene where every node is a person, and this is a fully connected graph. If you can compute a weight for the edges of the graph that tells you the likelihood of people being part of the same conversation, then you can use graph clustering algorithms to partition that graph and compute, which formations are happening at any given time, okay? Now, the key question is, how do you compute those weights, right? Now, in today's world, machine learning is you're here to help, right? It's your aid. And so one thing that you may be thinking is, well, let's throw this at a machine learning classifier, right? And indeed, this is something that people have tried in the past. And how you can do this is, you can say, well, I'm going to compute a function f to which I pass the orientation and the position x and theta for the nodes that are connected to the graph, to the edge to which I'm making a prediction. Say, if I'm making a prediction for edge ij that connects nodes I and j, I'm going to pass the position and orientation for people I and j. And then you can learn this function, say using weighted nearest neighbors, baggage trees, or logistic regression. And chances are you're going to do better than handcrafted heuristics that, try to predict that weight. Because if you have data, chances are you're going to better burn a classifier for this than you handcrafting your solution. Now, when we were working on this problem, one thing we realized is that when you're predicting a weight for an edge, not only the people that are connected to that edge tells you useful information, but actually the other people in the graph may also tell you useful information, right? And so for instance, right, it might be that it's a very crowded environment. And if that's the case, people are going to be standing closer to one another in general. If it's a less crowded environment, chances are they're going to be a little bit more away from each other. And so this helps you, information about everybody sort of helps you contextualize what's happening with the two people connected to that edge. And so we ended up sort of implementing this by expanding this formulation, by adding into the function that you're predicting social context, which is position and information, orientation information for everybody else in the scene. Now, the way we implemented this was with a neural network. And the key challenge that we ended up thinking about when we were implementing this was, okay, how do we learn a vector representation that works for this context, for the rest of the people in the graph? And you may think, well, this doesn't seem like a problem, right? You just pass it to your neural network. But it turns out that there's no specific order for people in a scene, right? Neural networks typically expect a set of ordered features, right? You don't sort of randomly change the order of your features when you pass them to your network. And even more, oftentimes you have a graph with, say, like here, 5 nodes. Sometimes you might have a graph with 10 nodes. How do you deal with a variable number of inputs? And so what we ended up doing here was using a deep set architecture, where the sort of key formulation here is first using a permutation invariant function that will not be affected by the order of the inputs. And so for instance, if you think about the maximum function, right? If you pass number 1 and number 2, or maybe you pass number 2 and number 1, you're going to still get number 2 as the maximum. And so by implementing a max pooling operation that reason about information about each people, you can make it permutation invariant. Now, to deal with variable number of people, there are many tricks you can play. The one that we use, which is particularly helpful here, is with max pooling, you could just repeat features for people, right? Because say that you have, 2 rows that are actually valid, but you have a slot for, say, 20 people input to your model. If you repeat the second row for everybody else, the maximum will always be the same, right? It doesn't get affected by having repeated rows. And so that kind of made this network work. And at least for me, impressively, it worked really well on a robot real time without any kind of temporal smoothing. And so I'm going to show you here a result using a Kinect camera to get features for people. Now, what you see here is the edges, which are in red, are darker the more likely people are of a group conversation. And then everybody's labeled with a color, where same color tells you the algorithm is predicting same group. And so as people come closer to the robot, which also has a tiny blue arrow right now, they are labeled as part of the robot's conversational group. As they're farther away, they're a different group. And as they move, these predictions sort of adapt to what's happening. And so yeah, main message here, as I mentioned before, is thinking about group phenomena, like those formations that happen during group conversations may be a way to, approach complex perception problems. for which perhaps you were thinking about different solutions like audio. In this case here, spatial behavior might be a way for robots to reason about conversational members. And so last example I want to show you is about robot perception and decision making. And so third idea from this talk is we can leverage structured data-driven methods to approximate complex physical and social phenomena in nature. One example, I think, is the work that I showed you before, right? Where we're taking advantage of this deep set architecture to enable the network to reason about that context for the problem. In other problems in robot navigation, we have applied sort of similar techniques to reason about traversability in human environments, right? Is it safe for a robot to keep moving forward? Or is it going to collide with something? We have applied this problem also to the context of more general navigation. And I want to show you one particular example in combining planning and deep learning to render socially appropriate navigation trajectories. And so if you were to implement a robot navigation system today, this is probably kind of a very standard way to do it. You would take a map of the environment, say like a 2D map. You have the robot's current location out of a localization algorithm, and you have robot's goals, so you can plan a path to that goal. Now, out of your global planner, you would get a plan towards that destination, and you would then adapt how the robot is moving based on sensor data, because chances are not everything is in the original map, right? Like people walking around. And then out of this reactive controller, what you will get is the velocities that you send for the robot, linear and angular velocity. Now, these days, with, again, advances in machine learning, several people have proposed to implement this reactive controller using what is known as imitation learning. So think about it as plain supervised learning, where I collect a set of trajectories of how the robot should move, given my global plan and my sensor data. And these trajectories tell me what velocity should be sent to the robot. And then, I use my favorite regressor to map, this plan and sensor data to my velocity controller. Yeah. Now, if you just throw this to your favorite neural network controller, chances are the local minimum the controller is going to get is not ideal. And to sort of combat this, what we thought was that adding structure to this controller would help. And the way we did that was by actually breaking it down into two components. A local planner that predicts a modification to the global plan, which we call a local plan, and also serves as additional supervision to get to a good set of weights for that model, and a velocity controller that finally outputs the velocities for the robot. Now, if this doesn't make much sense, I want to show you a video of what it means. So here you have a similar environment with people, with static obstacles, with a goal for the robot. You have the global plan, say, computed with A star to where the robot needs to go based on the map. And the robot now is going to use that neural network that I described before to predict a local plan, which is a modification of the global plan, and hopefully, get to the destination by outputting velocity commands for the wheels. And so if things are working, what you should see is that the local plan is adapting to dynamic elements like people, giving you a hint as to what the robot is going to do in the future, and also helping it get to the destination. Yeah. Now, one key question here is, how do you combine information from different input modalities for, say, your velocity controller? The first thing and most obvious thing you can try is just, you concatenate your features all together and the network should figure it out. But it turned out that depending on how many of these features you have in each case, the network might end up ignoring other features. And so instead of doing that, what we decided to do was try using attention mechanisms to learn how much attention should the network pay to, say, global plan or the LiDAR or the local plan. And so to show you here an example of what this means, on the left, I have a plot of how much the network is paying attention to each of these three components, LiDAR, global plan, and local plan. And this amount of attention is going to change depending on what the robot is doing. So as the robot starts, there's a person nearby, sensors become really important, LiDAR grows. When there's nothing, the local plan is the main thing that the robot is following. And then finally, when the robot starts reaching the destination, then at this point, the robot says, ignore everything else, I just care about my goal, global plan goes over. Now, the cool thing about this result is that we're not supervising these attention mechanisms. They're actually learned from data based on what the example trajectories were. Now, we did a quick test of this type of system on Jack Bravo. This is collaboration with Stanford. So this is the main Stanford CS building. And it was very surprising to me that at least this worked here, because everything we did from data collection from day one was all in simulation. And to me, the trick here is, we were using LiDAR sensors as our main sensor modality, and that's not too bad to simulate in comparison to other sensors. Now, if you want to, go this route and apply machine learning to this type of navigation controllers, I would say the first, challenge you would find is data. How do we get data, right? And this has gotten us a lot to think about, well, what can we do to scale data collection in human-robot interaction? And here's one potential idea that perhaps can help a little bit in terms of early system implementation. And this is what we called interactive online surveys. And so I'm going to explain what this means, but first let me sort of jump back to the context of navigation, okay? So to explore this idea, what we did was we created a simulation environment that we call SEAN, for Social Environment for Autonomous Navigation. SEAN is built on Unity, and it also connects to ROS so that you can ideally use it to test your full robot navigation stack in simulation. And on top of that, it comes with a bunch of people that move around using state-of-the-art cloud prediction, so that, if you're working in social navigation, you have people that are dynamically reacting to your robot. And also it provides a toolkit for navigation evaluation based on standard sort of quantitative metrics, like did you reach your destination, how close did you come to pedestrians, and so on. Now, this simulation built on Unity would naturally require a lot of hardware resources to run, right? Like a fancy GPU and so on. And what we want is to give a bunch of people access to the simulation so that they can experience what it would be like to interact with the robot, okay? And so to do that, we created infrastructure to deploy the simulation on AWS, on the Amazon Web Services Cloud Tools, and then render the simulations as part of a survey, as you see on this image on the left, so that people could interact with it on a regular web browser without having to have a fancy machine to do that. And so these are the type of interactive surveys that I mentioned before. Okay, these are surveys that include photorealistic simulations in which users can control an avatar and interact with the robot that navigates in the environment. And so the way we created the system is, we specify what kind of tasks we want the robot and the human to complete in the simulation. We put the simulation on the cloud, and then we render the graphics of that simulation onto a regular web browser. And then many people in parallel can experience these simulations and then via the survey tell us, what do they think about the robot? Was the robot working in a socially appropriate way, and so on and so forth. And so here's an example of what this looked in practice, a quick example. So this is a person controlling a human avatar, and there's a robot that is controlled in the back end by the ROS navigation stack in this case. And the person has to complete tasks, the robot has to complete tasks, and then we use this kind of as a way of doing a very quick user experiment to check how the robot is working. And so I'm gonna stop here. Hopefully I've gotten you excited about many ideas in human-robot interaction. I'm gonna recap sort of the 4 key insights that I mentioned today. 1, group phenomena provides novel mechanisms to drive group dynamics in HRI. 2, it also allows to computationally abstract some of the complexity of group interactions. 3, we can leverage structured data-driven methods to approximate complex physical and social phenomena. And lastly, interactive online surveys can help scale data collection during early system implementation and testing. Now, I started this talk sort of, telling you about these different research directions and a lot of our work. And looking towards the future, I'm really excited about potentially seeing them converge, in particular on studying group interactions in public settings. Right? If you think about it, in public settings, you cannot have a wizard behind the robot all the time. So you have to push for autonomy. These interactions, if they're in a particular place, they're going to lead to long-term social encounters. And at the end of the day, you can't really control who's in that space. So chances are you're going to have to deal with groups. And so, sort of thinking about the future, this is where we're going as a group in the long term. Now, shameless plug. If you're looking to join graduate school, then think about us. This is an example of a first robot that we built to study interactions in public. And so if this sounds cool to you, let me know. And before ending here, I want to thank all the many students, especially that have made this possible and our funding sources. And I'll leave you here with sort of a link to our lab and also a link to Sean in case you want to try it out. This is actually a very ongoing effort, pretty new, and we're looking for more people to get excited about it and help us build it for the community. Thank you.
Thank you, Professor. It was really, really great. I mean, I'm actually shocked that the robot abuse is so real. Like, I never thought that. I mean, yeah, we talk to our code when we code, like, what the hell is going on? But like actually seeing physical abuse to the robots was quite shocking.
Yeah, it's quite a surprise for me, at least. But I guess, as people become more familiar with these robots, right, it seems like why wouldn't be able to do that, right? In principle, the robots should be made to be safe, right? And oftentimes people assume, right, they're made for this, right? It's just kind of an assumption. It worries me though as a roboticist, right? Because if you break a sensor, I don't know what the robot would do afterwards. But this is something that I think we need to think smart about how we can, on the one hand, sort of teach people that they shouldn't be doing this, right? It's not like you drive your car, you break your car, and then you drive it again, right? Like normally you're like, oh, car is broken, right? I'm not gonna drive it anymore. And so that's on the one hand, and then on the other hand, from a robotics perspective, I think it's interesting to think, what is the safest thing robots can do to sort of stop that from escalating, if that's possible. And to us, sort of thinking about the social environment is one way to do that.
Yeah, I think we have one question. Yeah.
Perfect. We do have one question from Edward. This is a good one. So is there a way to learn more about how are we preventing robot abuse in public situations, or what does the future of that look like? Is it sounding an alarm, shouting for help, taking photos of the abusers, or what does that look like maybe for the future?
It's a great question. So I don't actually have a good answer because we don't yet know enough about what might be the most effective approach. I can tell you though, one of the motivations for work in that space came actually from the very first study that I showed from my PhD. So in that study, we had kids from very different age ranges, so all the way from 4 to 10 years old. And there were a couple of groups where around age 6, I'd say the kids were really, really exploratory. It was like they were, kind of mastering what happens if I take an action. How does the world respond to me? And some of these groups, they just wanted to like block the robot's eyes because they didn't know what it would do. They sometimes, try to kind of push it a little, see if it would move or it would do something, right? They were pretty much fearless. Now, me looking at this, I freaked out. I was like, no, don't do that. And of course, I didn't want to interrupt the experiment. So instead of doing that, what we did was we had the robot respond in 2 different ways. So first, the robot said, ouch. And I can tell you that did not work. It was really funny. The kids just laughed and laughed and laughed. Now, the second thing that the robot said was, please don't hurt me. And that didn't quite, work with the 6-year-olds, but there was one group where there was an older kid, and I think he kind of felt bad for the robot, and he pushed away the younger kids and kind of, calmed them down, and that allowed, sort of the interaction to continue. And that was actually our very first kind of idea of, maybe people around, can help the robot. And in fact, there have been other lines of work in HRI where that is precisely what the whole work is about, right? Can robots get help from people for physical tasks, for perhaps completing other tasks that people asked them to do, but they couldn't actually complete? And so, yeah, I think, the specific types of responses that the robot do can have both a positive or a negative effect, perhaps no effect in some cases. And so you have to be really careful about how exactly you do that. And to me, at least, it's really fascinating to think about how other people can potentially help robots to do this. And even in the way longer term, you know, can robots serve as a mechanism to help people deal with bullying, right? And so, you know, if you think about anti-bullying programs in schools, you know, one of the tricky things are, well, you know, you don't want to practice with another human, right? Because obviously you're putting a person in a bad situation, but you could totally practice with a robot, right? The robot doesn't really have feelings like a person does. And so could you use a robot as a teaching mechanism for these kind of strategies that actually help with human-human relationships? That's kind of another very, very interesting direction in the future. But yeah, what exactly it means from a practical perspective for robots long-term, I don't really know. I can tell you one more thing. So one big issue in several of the examples of what I showed as news of, you know, people mistreating robots is how the robots are introduced as a technology in a human environment. And so, you know, there's this particular example that kept in my mind of a robot that is like a police robot that was basically circulating on a street in, I think this was in San Francisco, where several homeless sort of treat that street as their home, okay, because they don't have a better place to live. And the company where this street is, that is a, you know, big building next to the street, they just didn't want to have people sort of staying on the street there. And so they put these robots to kind of help, right, not have people over there. Now, for the people that are homeless, that are living on that street, that robot is invading their home, right? It's like a threat to their normal living, if you think about it, right? And obviously, right, if you put a robot in that kind of situation, well, people perhaps are not incentivized to be nice to the robot at all, right? Because this is just affecting their way of living. And so a lot of these problems perhaps, you know, are occurring because of how we're introducing these technologies in particular human spaces. And you know, maybe we should be thinking more about what those consequences are and how are people perceiving these robots in their sort of, you know, day-to-day life. Mm-hmm.
Just a quick follow-up on that. Do you think because humans have this reaction to robots because they are perceived more like some threat to human or like a machine, and if the more the robots go towards like looking like humans or humanoids have different kind of behavior, or is it just robots in general?
It's possible, right, that different embodiment sort of means different perceptions of what's going on. That's definitely possible. So I must say, at least for our studies, the robots that we were using were really cute.
Okay.
You know, like the Cosmo robots are like, they're really nicely designed, and their expressions, right, when they express sadness, you're like, oh, you know, this is really sad. And when they're happy, you're like, oh, it's really happy, right? It's very easy to empathize with them. You know, and so I could imagine that perhaps a different robot that it just wasn't as easy to sort of get these feelings would be something that people wouldn't necessarily help, right? Chances are. And so we actually don't know, right? This is to my knowledge the only study that has tried this out. And it might be that, you know, if you change the robot, definitely the results are different. So I think there's more work to be done on that end.
That's really interesting. I think the human perception will be something that hopefully future studies will maybe reveal a little bit more on. So we have another question, one from Jill. She says, very interesting levels of complexity in various parts of the talk. How many students are involved, or how many conferences are usually attended or are presented at in a year?
Whew, I have to count. So, okay. So in terms of students, I would say oftentimes, you know, projects would have from 1 to sometimes 10 students. So it really depends on how long it takes to get something working. And so, for instance, I can tell you the work that I showed on navigation, that particular system, it took us easily a year to put together, if not more. And over the course of a year, many students got involved in the project. And so, you know, at the end of the day, when we submitted the paper, there were a lot of authors there. There are other projects where, you know, it's kind of more easier, more direct to sort of get the kind of result you want, and sort of the amount of human effort that you need for that is way less. And, you know, easily you can go down to 1 student. in those cases. Now, in terms of the size of our lab, right now we are 3 PhD students, sort of full-time, many other PhD students that collaborate with us here and there, and many undergrads at Yale. We're getting 2 more PhD or so, maybe 3 PhD students this year, and we're kind of growing, so more people along the way. And how many papers, I don't know, it varies along year to year, but you can imagine, if you wanted to go to grad school, my personal opinion is, you should be shooting for ideally 2 papers a year, if possible 1 paper a year. And so, you can multiply sort of, number of students by number of papers a year, and that kind of gives you a sense of how things work. Of course, this is my own personal opinion. Every research lab is different. So if you're thinking of grad school, definitely check with kind of the specific people wherever you're applying.
Yeah, just like I totally agree. It's kind of very specific to the labs. So again, follow-up question for this one. How does like an ideal grad student for you look like? So maybe someone in the audience can help with this. So if you're looking.
So this may sound very generic. It's not on purpose. It's actually true. So I would say an ideal PhD student is a hardworking person who's very perseverant and curious. And yes, I know this sounds very generic, but for the most part, in the time of a PhD, what you're doing is trying to understand things that perhaps nobody else in the world has ever thought of. Yeah, and if you think about it that way, chances are the first thing you try is not going to work, because they're difficult problems. You might be wrong, who knows. And what this means is that you just have to keep trying. And the curious part comes because at some point, right, when you're finishing your PhD, you want to effectively be what is considered an independent researcher, which means that you are the one who asks the questions. And I feel like asking these questions comes sort of naturally if you're a curious person. Of course, there's people who are not curious, who can be trained to ask good questions. But if you're a curious person from the beginning, you're always going to be asking questions. And so it's just going to be very easy for you to do that once you go on, start your lab or work in research in industry or whatever you want to do. And so, yeah, I would say those are probably the key qualities. Now, everything else, all the details of what what have you done so far, for the most part, if you're hardworking and you're curious, you learn whatever you need to be successful. So those things don't really worry me too much.
That is definitely helpful. I could say that. I guess is in general, being curious is so much helpful to learn more about stuff. So
yeah, so I would say, if you're a student somewhere and you're shy to ask questions, you should stop that and you should start asking more questions. And that's a good start to eventually get to grad school.
I agree. I do have one more question for you. So while in the slides, there was one slide where the robot was giving color schemes to people and appointing them to groups. So
say it again.
Like the robot was, when the robot was perceiving people around it, there was a color scheme given to them. Like,
yeah, this one, right?
Yeah, this one.
If I play this.
Yeah. So
yeah.
what the colors mean?
Let me explain again. Sorry, I went over this too fast. So
I guess I did not understand.
No, it's fine. So everybody here is a node in the graph that I described before, including the robot. The robot is a node too. And the edges are these lines that we're plotting in red. The darker the edge, the more red, the more likely people are part of a group conversation, okay? Now, these edges by themselves, they don't tell you groups. They tell you pairwise relationships, right? Because they're connecting 2 nodes only. And so what we're doing to indicate the groups is we're labeling the nodes, basically the people we're rendering, and the robot with a given color. So whoever has the same color on a frame is said to be part of the same group. And so right now there are 2 colors. So there's the robot that has this kind of cyan color and these two people, and that's one group. And then there's these other two people over here that have a darker blue color, and that's another group. And if I keep going, it gets a little bit confusing because there's no temporal smoothing, right? So the colors from one frame to the next might totally change, but as long as people or nodes have the same color, they're meant to be part of the same group. And so, you know, like here, I'm gonna pause. This is one group, and then this is another group. And sometimes, of course, also people come and go, like this person over here, because they're occlusions. And if the Kinect, right, doesn't see her anymore, she whoop, goes away. And so that's why also sometimes it's right there, right? It's kind of hard to tell what's going on. Right now, again, I'm gonna pause. There's two groups. There's this person over here, and then the robot, and then there's this group in the back. And this person back here, who's actually not detected, is not down here because it's too far from the Kinect.
It depends on the distance, I guess.
Yeah, so that's right. So we're using the Kinect skeleton to get people's position and orientation. And so if someone is too far, like this person over here, then you wouldn't get to see, you know, where they are in the kind of robot's view of the world. Yeah, sorry, I went too fast over this. So by the way, the other thing that is useful to sort of think about here is this is on the left, the Kinect's view, so it's stationary. On the right, you have the robot's view. And so we're not using right now the robot's view, even though you could, but it was just easier to set this up with a static camera. So you wouldn't have to worry about the frame of the camera moving around.
Oh, okay, interesting. Thank you. Yeah,
Yeah, no problem.
Thank you so much, Professor. I think we're nearing the end of our session. Thank you so much for coming out tonight and taking the time for so elegantly explaining and abstracting from the key motivators and jumping into the learning techniques used. That's always a difficulty, but it was really fun and presented in a really easy to understand manner. I would have loved to attend this in person. Your energy is contagious.
I agree.
Yeah. And thank you so much for the audience as well for coming out, and make sure to check our upcoming events. Link will be provided in the chat. Thank you so much, everyone.